to start with a sort of a personal story. There is a famous paper in number theory. It's really a landmark in number theory. The title is Modular Curves and the Eisenstein ideal. By Barry Weiser, and it was published in 1977 in the publication Mathématiques de l'IHS. So it's a very rich and long paper with many side questions, and in particular there was a sort of an obscure question in that paper, and as it happened, while I was a graduate student, I was told that maybe I could give an answer to this obscure question. And indeed, I gave the answer, and I'm going to tell you what is the answer. So the point is that the question was formulated just out of general principles. So you take n a prime number, and Weiser defines, as I said, out of general principle, a number modulo n. And here is the essential answer that I gave. The answer is, so I'm not going to explain, at least not right now, how you can define the number, but the outcome is, after a non-straightforward calculation, k to the power of k modulo n. So this belongs to z and z star. Well, this is a sort of a coarse answer. The fine answer is a little bit more precise. So denote the number by square root of u, and it's actually theta times epsilon times actually this number to the power minus 4. So what are epsilon and zeta? Zeta is 1 if n is not congruent to 1 but 3. And it's 2 to the power of n minus 1 over 3 if n is congruent to 1 but 3. So in any case, it's a cube root of unity, and epsilon is the square root of unity. So it's minus 1 if n is congruent to 1 mod 8, and it's 1 otherwise. So, well, at the time, so I gave this answer in my thesis, in fact, around 1993. And I got compliments from Weiser and from my advisor, but except for that, nobody cared about this. I did other things, and every time I was invited, it was suggested that I would speak about something else. So at the time, I practically made no publicity for this, and as it happened over the last few years, there has been some progress around this number. So let me comment about this from an elementary point of view. So the first question the first remark you might have is, well, why take the product from 1 to n minus 1 over 2? Why not go all the way up to n minus 1? So if you go all the way, course, you can regroup k with minus k modulo n, and essentially they cancel each other, so you get the power of minus 1. Plus or minus 1. Even you can say it's minus 1 to the power, let me see, n squared minus 1 over 8. Okay, so this is not very interesting. So you might actually want to compare this to a classical elementary number theoretic statement, which is called Wilson's theorem. In fact, it has been proved by Lagrange, which says that if you take the product of k, this is factorial n minus 1, and this is actually congruent to minus 1. There is a sort of a finer thing, which is due to Merel. Merel was an American mathematician who worked in Britain a century ago. And what did he prove? So yeah, you can take factorial n minus 1 over 2. You can square it, and what you get is minus 1 to the power of n minus 1 over 4. I think that's it. Yes. And so if n is congruent to minus 1 mod 4, so this is easy to prove. The real statement is coming now. So if n is congruent to 1 mod 4, minus 1 mod 4, so this is plus 1. And therefore, this factorial, mod n, so this is mod n, of course. This factorial is plus or minus 1. And if n is congruent to, yes, in that case, it's plus or minus 1. Then it's minus 1 to the power of, let's see, 1 plus h of square root of minus 10 over 2. So what is h of square root of minus 10? It's a class number of the field q of square root of minus 10. So if you are not familiar with class numbers, it's something which is the order of finite groups, the class group, and the class group measure actually the extent to which you have unique factorization in that field. So you can see that already we are seeing some sort of elaborate arithmetical content in those sort of numbers. So a remark, which is not easy to see, but it is true, about square root of u. Square root of u is always a 12th power. So the question now, and this is actually what is the content of the arithmetical content of this number is whenever this is more than a 12th power. So for p prime, which divides n minus 1 over 12, when of course, if p is a prime power which does not divide this, this is always a p's power. So, the question is not interesting. The question is interesting when p divides. When is square root of u 12 p? Okay, so now if you play a little bit with this formula, you easily find the following thing. For instance, the root of u is a fifth power if and only if take this factorial and you divide out by square is a fifth power. What about the third power? So I recall that we know that this number is a cube because it's a 12th power. So the question is whenever it is a 9th power, if and only if. So that would suppose that n is congruent to 1, not 9. If and only if is a cube. So it's always mod n, of course. And then there is a question of whenever it is an 8th power, if and then the criterion is that factorial n minus 1 over 4 is a square. Okay, and there is an additional criterion for this last condition, namely that 8 divides the class number of square root of q of square root of minus n. Okay, so you can see that there is this connection between the question of whether this number is a piece power and certain more subtle arithmetic environment. About 20 years ago, Caligari and Emerson went a bit further. Let's suppose p is greater than 5. So if the p part. So you see, here we were looking at the divisibility of the class number by powers of 2. Now we are going to look at the divisibility of the class group by powers of p. And specifically, if the p part of the class group of q, so this time we take the field generated by the piece root of n. So the p part of the class group is non-cyclic. Then is a piece power. Always what n. This is not at all elementary. I mean, the notion of class group is something you learn in pre-graduate school. And, but the proof of this is quite important. Okay, so about a decade ago now, I think I suggested to Emmanuel Couturier to work on these questions. And I'm going to mention, of course, you know him, and I'm going to mention a few of his results. So, initially, I suggested to him this topic because I wanted to understand better the work of Caligari and Merel. But here is something that he did. So I might ask, well, what sort of prime number do you know? So suppose you were asked to produce a very large prime number. Of what shape would it be? So if you look at the tables of the largest known prime numbers, of what sort are they?
Check some Mersenne prime.
Good, Mersenne prime, yes. So suppose N is a Mersenne prime. About, I think, about 50 Mersenne primes are known, I think. And of course, there is a sort of a competition to find the largest prime numbers, and most of the time, Mersenne prime is. So suppose, so N. So note that in that case, if you look at n minus 1, so that n minus 1 is 2 to the p minus 2, and that is divisible by p by Fermat's little theorem. So then p divides n minus 1. P is prime, of course. Then, this is the piece power. An example of this is n equal 31 and p equal 5. So the sort of the generic situation is rather that the square root of u is not a piece power. But for Mersenne primes, it happens every time. And so this is a completely elementary statement, but I don't know any elementary proof. And in particular, so this number is a piece power, but you might ask a power of what? Then there is no closed formula for the piece root of this number. Here is another connection that you might find surprising. Consider the Jussieu polynomial. It's defined as follows. Depends on the prime number n, and this is the sum from I to 0 to n minus 1 over 2. So this is the binomial coefficient squared. And you take it mod n, so it belongs to of course the definition is elementary, but there is a particular use of this polynomial. So lambda in Fn bar satisfies. So the roots of this polynomial are precisely the lambda, such that if you take the elliptic curve, so it's an elliptic curve over finite fields, and there are two types of elliptic curves over finite fields. There are the ordinary one and the supersingular one, and there are finitely many supersingular ones. and they correspond precisely to the roots of the Jussieu polynomial. Super singular. But you don't need actually to know anything about elliptic curves to appreciate what I'm going to say. You can, what Couturier showed, is that if you take, you can compute the discriminant of this polynomial. And this is precisely, well, not precisely, but essentially, minus 1 to the power of n minus 1, n minus 3, yes, over 8, divided by factorial. So recall that all this is plus or minus 1 times the product from k equal 1 to n minus 1 over 2 of k to the power of 4k. So essentially, this is the same thing as square root of There are several proofs of this. There is one elementary proof which relies on a differential equation. And the differential equation is as follows. For lambda times 1 minus lambda, hn, n plus 2, plus for 1 minus 2 lambda, times n plus 1, hn, n plus 1, minus 2, square n 0. So for any n greater than 0. So hn, you can check that hn satisfies this differential equation, and once you have the differential equation, you can play with it and you can compute the discriminant and you get this formula. But this is one of two possible proofs. Okay, so this is a list of sort of funny properties of this number. Now, I will try to tell you something about the nature of this number, its significance. So the question is for p prime, whenever we have said that consider a discrete logarithm with value in the field with p element of p. So projective. So just a group homomorphism which is surjective. Then this is the p's power. If and only if its logarithm is the p's power. If and only if this is 0. But in term, so leave aside the square root and cube root of unity, this amounts to sum of k p of k equals 0. Okay. So let's try to find the meaning for this. Suppose I wouldn't sum over integers mod n, but over ordinary integers. And this is a usual logarithm. And you might ask where to stop. Well, why not stop at all? Okay. What is this? Or what could this be? I'm sorry?
Gamma function.
Not quite. Not quite gamma.
Gamma 2.
Gamma of 2.
No, not gamma 2. There's two types of gammas.
Yes.
But if you remove the coefficients, the gamma, well, it's without coefficient k, it's square root of 2 pi.
Oh yes, you would say yeah. Okay, you would have a factorial, but no, I insist on having k. Okay, so you know the standard riddle. That sum from k equal 1 to infinity of k. So you have seen that, I'm sure there are YouTube videos about this. This is minus 1 over 12. This is what Euler discovered, I think. Because if you take an s here, then you have the zeta function. And the value at s equal minus 1 of the zeta function is minus 1 over 12. So, okay, so if the sum of the k is the value of the zeta function, this is the value of the derivative of the zeta function at s equal minus 1. Okay, so that would be the derivative of the zeta function at s equal minus 1. So I'm going to try to explain to you why this square root of u is some sort of incarnation of zeta prime of minus 1 in the finite world of the field with n elements. I think this has been noticed by Caligari and Venkatesh. Actually, if I want to be a little bit more precise, the fact that square root of u is a 12th power has to do with the denominator 12 here. And in fact, the thing to realize is that the analogy is rather with exponential of zeta prime over zeta of minus 1. If you put zeta of minus 1 in the denominator, its inverse would be 12, obviously, and so you get a 12. So this is a sort of a better analogy. So in what sense? So this analogy can be made actually a bit more precise in the following way. Okay, so let G is a group Z and Z. And you consider C bracket G the group M. So in particular, if you take an integer n, then you can consider bracket n. So you reduce n modulo capital N, and you get an element of G. And so this belongs to C and G. Of course, except if capital N divides N, in which case this is simply 0. Okay. And now here is an analog of the zeta function. Let's sum from n equal 1 to infinity of bracket n divided by n to the s. You can factorize this. This has an Euler product. Yes. So you can expand this formally and you get this. So it's a little bit deeper to express. Well, you can show that this admits analytic continuation and so functional equation, and you can also compute the values of integers of this function. This was essentially done by Eric, I think. Long below. And for that, consider P2 bar, which is a function from R to R, not periodic, and which to T associates T square minus T plus 1/6 if T belongs to 0, 0, 0, 1. So what I said, otherwise it's 1 periodic. And the formula is the following. Minus sum T equals 0 to n minus 1, yes, 1/2 P2 bar of T n bracket T. No, that's correct. Okay, that's correct. Okay, so this is equivalent to computing the values of the Dirichlet function at -1. Okay, and the first thing you can note is that if you take the value at take the sum of the values of theta t of minus 1, so then 1 has. So you take the sum of the values. Is n minus 1 over 12. So almost the value of zeta minus 1, but this term n over 12 appears. And so a priori, this would belong to C bracket G, but in fact the coefficients are almost integers, and in fact inside you have, let me see, Z. So the prime number which might occur in the denominator are just come from the 6 here, from the n here, and the 2 here, so the coefficients belong to 1 Z bracket 1 over 6n, so bracket B. Okay. So you have a group ring, and let me see. Yes, you can take the image now. Of zeta g of minus 1 in. You take the ideal, which is generated by n minus 1. Well, let's call this R. R n minus 1. Yes. So now consider the augmentation map. Shall I do that really? N minus 1 over. Okay, I'm a little bit imprecise, so let me be more precise. So n is going to be the numerator of n minus 1 over 12. So I'm going to divide out a little bit more, like n here, and here r about n. And which goes to R mod n, which simply with 2 bracket G associates 1. Okay, so because of this formula here, the image of this element in that ring is n minus 1 over 12, which is 0 modulo n. So, so the augmentation map vanishes on that thing. And the kernel of this map G is the augmentation value. So now you need, so you have an element which vanishes modulo the augmentation ideal, and the natural thing when you have something which vanishes modulo an ideal is to look at its class modulo the square of that ideal. This is what we are going to do now. So use, there is a standard fact which says that if you take an augmentation ideal modulo its square, this is isomorphic to And since we have inverted out the prime number 2 and 3, we need actually to 6, or n doesn't matter, so this actually coincides with the part of G when you kill the 2 and 3 prime number. And how is this given? So to an element G, so 1, you associate simply the class of G minus bracket 1, bracket G minus bracket 1. Obviously, this is in IG because the augmentation map of this is 1 minus 1, 0. Okay, and this is actually an isomorphism, which is an easy exercise. Okay, so now, what is the image of zeta G of minus 1 in that thing? So to recall, this is simply Z over NZ star modulo the 2 primary and 3 primary parts. Okay, so I guess you can see where I'm going. So you can make the calculation, actually, following this rule. And what you get is the following thing. So then, so the image then of zeta G would be zeta G prime. So taking the image modulo the square of the augmentation ideal is like actually taking the derivative of it. Okay, and suppose this thing would vanish, would be in the second power of the augmentation ideal, then we would like to look at it modulo the cube of the augmentation ideal, which would be like taking the second derivative. Okay, so you can do the calculation. And so this to the power of 6 is equal to and minus 1 of 2. Okay, to the power of 4. Okay, so you recover actually the number of introduced at the beginning by this calculation. So I am about halfway through my talk. So this is sort of the end of the first part, and the second part will be a bit more advanced. I'm going to recall the basic things, but it will be about modular forms. In any case, so this is what justifies the analogy with the value of at minus 1 of the derivative of the zeta function. So this sort of derivation is sometimes called razor-paid derivative. But I'm pretty sure that people have been doing that